The dielectric is a mysterious material that goes between the plates of a capacitor and makes them even more effective. If you want to know how this works clearly and simply, then watch this video. Some molecules, known as dipoles, have an uneven distribution of charge around their outside or perimeter. This means that in effect they have a tiny little negative at one end and a tiny little positive at the other, and the smallness of this is indicated by the little lowercase delta symbol there. So this charge is actually less than the charge on a single electron. These dipolar molecules actually have a pivot or rotation point in their centre, which means that we can rotate the molecule one way or the other, and it's this rotation along with the tiny charge distribution that makes them so important in dielectrics in capacitors. As you can see, within a normal dielectric material which is placed between the two plates of a capacitor, the dipoles are arranged completely randomly. Imagine now a very simple circuit made of two metal plates with an air gap between them and connected in series to a switch and a cell. As the switch is turned on, charges will flow onto the plates of the capacitor, and this in turn means that a potential difference will develop across the plates of the capacitor. After a short while, the PD on the plates is equal to the PD on the cell. Therefore, there is no difference between them and no more charge flows. So the capacitor is fully charged. Because our plates are charged, we now have an electric field running from positive to negative between the two plates. The size of this electric field strength E is given by the voltage on the plates divided by the distance between the plates. Let's imagine now that our capacitor is completely discharged and we're going to insert the dipole material between the plates. As we turn the switch, of course, the capacitor will charge up, meaning the electric field will be re-established between the plates. And it's at this point that the dipole begins to work its magic. This is because the negative end of the dipoles is going to be attracted to the positive plate, and the positive end of the dipoles is going to be attracted to the negative plate. Therefore, the dipole molecules will all rotate and line up, as you can see. Because the dipoles are charged, there is a tiny electric field running from the positive to the negative end of each dipole. After closing the switch and all the dipoles are lined up, we now can see that we have many very tiny electric fields all pointing in the same direction, and these tiny fields add up to something really quite significant. We can see as well that this significant new electric field is in the opposite direction to the electric field that we originally had from the capacitor plates. Hopefully you can now begin to see why it is that a dielectric enables a capacitor to store more charge. Part of the electric field from the plates of the capacitor pointing downwards is cancelled out by the electric field from the dipoles pointing upwards, and this means that E, the electric field strength, has been diminished a bit. Given that the distance between the plates has remained constant, if E goes down, that means that the voltage across the plates has also got to go down. So we're now in a situation where the voltage across the plates, which was equal to that on the battery or the cell, has now diminished a bit, meaning there's a potential difference between the cell and the capacitor, and so more charges can flow onto the capacitor. And if more charges flow onto the capacitor, the electric field gets stronger, and eventually we reach a place again where the voltage across the capacitor and across the cell are once more equal. And at this point, current will stop flowing and the capacitor is again fully charged. But of course, the magic thing is that we now have considerably more charge on the capacitor because of the dielectric than we would have had. The effect of the dielectric then is to reduce the electric field strength produced by the parallel plates, enabling more charge to flow onto the capacitor. And hey presto, we have increased the capacitance of the capacitor. Neat, eh?